Today we're going to talk about expanding and condensing log expressions, and we're going to tackle a few more difficult exponential equations. So we've learned the three log rules, the power, the product, and the quotient rules. And what we're going to do with those rules is we're going to take a logarithmic expression and expand it. You did this in Algebra 2 quite a bit, but some of the examples that we'll do today will be a little bit more difficult. So let's say you have a natural log of the square root of x squared plus 3x minus 10 over x squared minus 3x plus 2. And we're asked to expand that log. So to expand that log, we're going to write it as the sum and product of multiple log terms. So the first thing we're going to do is we're going to notice that these two expressions are factorable. So that's going to turn into the natural log of the square root of x plus 5 times x minus 2 over x minus 1 times x minus 2. So the x minus 2's will cancel out, and we're left with x plus 5 over x minus 1. And when you take the square root of that, that's raised to the 1/2 power. That's what the square root is. So this will be the natural log of x plus 5 over x minus 1, all raised to the 1/2 power. And when you have a power, you're going to drop it down in front of the log expression, so the 1/2 becomes a coefficient, and that goes away. And then you have a quotient rule that you're going to use. So this turns into 1/2 times, parentheses, you're going to do the natural log of x plus 5, which there's no rule to expand that. You're going to subtract from that the natural log of x minus 1, and then close up that parentheses, and that's going to be the final answer. So you could have done that last year in Algebra 2. Here's another example. Let's take the natural log of the cubed root of x minus 1 times 3x minus 2 to the 4th power over x plus 1 times the square root of x minus 1. And we're going to raise that to the 2nd power. So we can do these a number of ways, but what I would do first is I would recognize that you've got an x minus 1 on the top and the bottom that you can rewrite as a fractional exponent. So we'll have this become the natural log of, and this 2 can move out front right away. Let's get that 2 all the way down front here. So we'll have 2 times, and then that goes away, the natural log of, and this x minus 1 is to the 1/3 power, 3x minus 2 to the 4th. And then this minus x minus 1, I'll just move it over there so they're on top of each other. And this is to the 1/2 power and times x plus 1. Now we have the same base, and when you divide with the same base, you subtract exponents. And since the bigger exponent, 1/2, is bigger than 1/3, we're going to subtract 1/2 minus 1/3. 1/2 minus 1/3 is 1/6. So this becomes 2 natural log of that 3x minus 2 to the 4th stays on the top. The x minus 1, subtract the exponents, becomes 1/6 on the bottom. And then that x plus 1 just stays by itself. So now we can expand this using the quotient rule and the product rule. So this becomes 2 times the natural log of 3x minus 2 raised to the 4th power, and you're going to subtract from that, and what you can do is you can open up parentheses and have the sum of those two logarithms. This minus sign is going to distribute through these two terms, so all I'm going to do is I'm going to take the natural log of x minus 1 to the 1/6 power. Anything in the denominator will have a subtraction in front of it, so that's minus the ln of x plus 1, because both of these terms are where in the denominator they both become negative after you use the quotient rule. And then the only thing left to do, oops, I should have put a big parentheses around there. The only thing left to do is drop the 4 down front, the 1/6 down front, and then multiply everything by 2. So this becomes 2 times 4 ln of 3x minus 2, which is just going to be 8 ln of 3x minus 2, minus 2 times 1/6 ln of x minus 1. 2 times 1/6 is a third, so this is minus 1/3 ln of x minus 1, and then this 2 distributes over there, 2 times the ln of x plus 1. So we've expanded that as much as we possibly can. And the opposite of expanding is condensing. So let's condense a log. Let's condense 1/3 ln natural log of x squared plus 4 minus 1/2 natural log of x squared minus 3 minus the natural log of x minus 1. Well, any log term with a subtraction in front of it, this is going to become one argument. We're going to condense 3 logs into 1. So we're going to use the opposite of what we did above. That 1/3 is going to become the exponent on x squared plus 4. The 1/2 is going to become the exponent on x squared minus 3. And then the 1/3 power is the cubed root. So this is going to be the log of the cubed root of x squared plus 4 minus the log of the square root of x squared minus 3 minus the log of x minus 1. And so now that the arguments are all singles, you can just condense that into one single logarithm. Any positive term, that argument goes in the numerator of the fraction. So the cubed root of x, the cubed root of, can you see that? Maybe a little bit better. All right, here we go. The cubed root of x squared plus 4 is on the top, and the square root of x squared minus 3 is on the bottom, and that gets multiplied by x minus 1. It also goes in the denominator because of the negative in front of that. So that's totally condensed. Next thing we're going to use is we're going to use these log rules to evaluate an expression. We're going to evaluate a log expression, and this is going to be the log base b, don't know what that is, it's just a b, of the square root of x squared over y cubed z to the negative 5 power, and that whole expression is going to be raised to the 6th power. We're going to evaluate that given 3 facts. The first fact is that the log base b of x is equal to 0.46. The log base b of y is equal to 1.07, and the log base b of z is equal to 0.73. And this is going to come out to be a number after we expand it and then substitute these values in. So what our job is to do is to expand and substitute. So right away I notice that I've got a square root, so that's the 1/2 power. So this is a log base b of x squared over y cubed z to the negative 5th power to the 1/2 power, that's the square root, and that whole thing gets raised to the 6th power. My power rule says that I'm going to multiply those exponents 1/2 times 6. I'm just going to multiply those together and get a 3. My next rule of exponents say that I'm going to multiply each one of those exponents by 3. So this becomes the log of x squared to the cube to the 3rd power is x to the 6. y cubed cubed is y to the ninth, and z to the negative fifth. Whoops, that's a z. Z to the negative fifth, raised up to the third power, z to the negative 15th. That's log base b. So the next thing we're going to do is we're going to expand that out. Actually, I think I'm going to move this z to the negative 15th up to the numerator and call this log base b of x to the 6th, z to the positive 15th over y to the 9th. And now we just expand that out. So this becomes a log base b of x to the 6th plus log base b of z to the 15th minus log base b of y to the 9th. The power rule says that we're going to move the 6 down in front, move the 15 down in front, and move the 9 down in front. And our last step is to substitute these values into those log expressions. So this becomes 6 times log base b of x is 0.46 plus 15 times log base z is 0.73 minus 9 times log base b of 9 is 1.07. And if we put that into our calculator, I think I did this right. You can try it. It would be wonderful if you would. This turns out to be 4.08. So that is the evaluation of that original expression given those log values and using some expanding. All right, the next thing we're going to do is solve some exponential equations, solve some tricky ones. All right, the first tricky equation is going to be this. E to the 2x minus 4e to the x minus 5 is equal to 0. We'll solve it algebraically, and then we'll look at the graph and solve it graphically. So I'm going to be solving these for x. That's our variable. And what I can do is, in this kind of situation, this looks like a quadratic equation to me, and it will be if you let u be equal to e to the x power. And what we have is if we square u squared is equal to e to the x squared, and e to the x squared, multiply those exponents, you'll get e to the 2x. So in this expression, when I have e to the 2x is the same thing as u squared, when I have e to the x, it's the same thing as a u, and the 5 stays a 5. And if I wanted to solve this for x, if u is equal to e to the x, solving this for x, you take the natural log of both sides, then the natural log of u is equal to x, and I'm going to have to use that when I solve this equation. So what I'm going to do is substitute e to the 2x with a u squared. E to the x gets substituted with a u, and what we have is a quadratic equation like we've solved from Algebra 1. Factors of -5 that add up to -4 are u minus 5 times u plus 1. So we have u equals 5 and u equals -1. But we're not solving these for u, we're solving for x. So in order to solve for x, I know the natural log of u is equal to x. So if u is equal to 5, we have the natural log of 5 is equal to x. And if u equals -1, we have the natural log of -1 equals x. But we can reject that because we can't have a negative argument for a logarithm. So if we take the natural log of 5, just plop that into our calculator, we get, you can either leave it as natural log of 5 if you don't have a calculator, or if you do have a calculator, 1.609 would be the approximation to 3 decimal places. And if you wanted to put that into your calculator and check your answer, you can put e to the 2x minus 4e to the x minus 5. And if you look at the graph of that, the 0 is the x-intercept. So if I calculate that, it should be the same value that I got here, 1.609. So second, calculate 0. You should be trying this on your own too. Left bound, right bound, enter, and 1.609 is the same answer that we got before. So this is the graphic solution, and there's the algebraic solution. A similar question to this, or a similar example, is if we have a problem like this: 100 to the x minus 10 to the x minus 2 is equal to 0, and our job is to solve for x. So we have a similar situation because 100 can be rewritten as 10 squared. So what we're going to do is we're going to write this as 10 squared to the x, which is 10 to the 2x, minus 10 to the x minus 2 equals 0. And then we have a similar situation to the other one. We're going to let u be equal to 10 to the x, which means u squared is equal to 10 to the 2x. And if I wanted to solve this for x, I'm going to take the log of both sides. So the log base 10 of u is equal to x. And we're going to use that when we evaluate this at the end. So this becomes u squared minus u minus 2 equals 0, which is factorable. And if we solve, we get u is equal to 2, and u is equal to negative 1. So if we wanted to solve for x, x is equal to the log of 2, and x is equal to the log of negative 1, which we reject because you can't do the log of a negative number. So now we have the log base 10 of 2. Oops. And so our x value is 0.301 approximately. And if we put that in our graphing calculator, 100 to the x minus 10 to the x minus 2. Take a look at that graph, calculate the x-intercept. Second calc. Left bound, right bound, and 0.30301 is the answer that we get here. It's the same as the algebraic answer. Here's a tricky one. Let's say we have the ln of 3 minus x squared is equal to 7. If we want to solve this natural log problem, we can rewrite this exponentially as e to the 7th power is equal to 3 minus x squared, because this is log base e. And so if I add x squared to both sides and subtract e to the 7th from both sides, we get x squared is equal to 3 minus e to the 7th. So x is equal to the square root of 3 minus e to the 7th, plus or minus. But when we look at our calculator and we do the square root of 3 minus e to the 7th power, we're going to get a non-real answer because 3 minus e to the 7th is a negative number. And since this is a negative, you can't take the square root of it. So you can't take the square root, so there is no real solution for this problem, and you can stop right there. And then one more example I'm going to do, and this is an exponential expression that I want you to solve for t in terms of y. Solve for t in terms of y. And this looks similar to the question that we did, question number 90, I think it was in class. Y is equal to 3,000 over 1 plus 2e to the negative 0.2t. And if I want to solve this for t, this is the similar situation that we had in class today. I can put a 1 underneath the y and cross multiply. Or I can also just swap positions of the y and this denominator. So this actually becomes 1 plus 2 e to the negative 0.2t is equal to 3,000 over y. And now we just have just a couple of algebraic steps to do. You want to get rid of that 1 first, so you're going to subtract 1 from both sides. So there goes the 1. The next thing you're going to do is divide by 2 to get rid of that 2. So we're going to take that and divide the whole thing by 2. So now we have e to the negative 0.2t is equal to this expression. To get rid of an e, we're going to take the natural log of both sides. So negative 0.2t is equal to the natural log of 3,000 over y minus 1 divided by 2. And then to solve this for t, we're going to just divide both sides by negative 0.2. So there's your t value solved in terms of y. So if you were given any value of y in the beginning, like if y equals 4,000 or 10,000, all we have to do is substitute it into this expression. Or we could put this in our graphing calculator under y equals and just plug some values in and try to get some specific things here. So the only thing left to do, I think, is I'd like you to try one on your own before class tomorrow, and let's see what you get for this equation. So this is going to be your turn to do on your own. I want you to solve for x. E to the 2x minus 4 e to the x plus 3 equals 0. I want you to solve it algebraically. And then check graphically. Let's see what you get. And we'll talk about that tomorrow.